So, good afternoon, everyone. I think we were discussing regarding, we have started the new chapter that was atoms. In yesterday's class, I think we have discussed regarding the different structure of atoms given by J.J. Thomson. Then we have discussed regarding Rutherford model of atom. Then we have studied about the defects of Rutherford model of atom. Later on, we went to Bohr's model of atom. What are the postulates? Bohr's postulates. Then we have discussed regarding the limitations of Bohr's postulate, and the explanation for the quantization rule of Bohr's model was given by de Broglie. This all things we have discussed in yesterday's class. Now let us start today's class with the last important SAQ from this chapter, that is different types of spectral series in case of hydrogen atom. So what is our first topic? Today's last topic of atom. Different types of spectral series different types of spectral series in hydrogen atom. In hydrogen atom. Actually, yesterday we have seen regarding one of the defects of Rutherford model. What was the defect? According to Rutherford, electron is accelerating around the nucleus and it should continuously emit the radiations and we should get the continuous spectrum. What the scientists have observed, they have observed that the spectra is what? Discrete spectra. So let us see how we are getting the discrete spectra in case of hydrogen atom. How do we get spectral series actually? See here. Let us assume few energy levels. Assume that we are having energy levels. I am just explaining, I am not starting the answer. Let us assume that these are the energy levels. There is one electron in highermost orbit. Here we are having one electron. Now, if the electron is coming down towards the lowest orbit, assume that this is n is equals to 1, this is n is equals to 2, this is n is equals to 3. Whenever this electron is jumping from any of the higher energy orbit to lower orbit, what will happen? It will emit some energy E is equals to h nu. And whenever it is emitting some light, that light should have some wavelength. That photon is coming outside. That is nothing but the light is coming outside. So it should have some wavelength. So that wavelength depends upon from which level the electron is being jumping. Whether the electron is jumping from third level to first level, the electron is jumping from second level to first level, or the electron is jumping from some infinite level to first level. Based on that level, transition level, the wavelength of that particular light depends. Now we are going to obtain the spectral series in case of what? Hydrogen atom. And we know that hydrogen consists of one electron. So let me try to draw the thing. Let us assume this is the nucleus. And we know that what we know, electron revolves around the nucleus in which orbit? Circular orbit. Electron revolves around the nucleus in which orbit? Circular orbit. So let me consider those circular orbits. So let me consider those circular orbits. So these are the different circular orbits. And here we are having nucleus. Nucleus will have positive charge. Let us assume that there is one electron revolving in this orbit. What are the level of this orbit? This is n is equals to first level. This is second level. This is third level. This is fourth level. Now, whenever the electron is revolving around the orbit, in which level, fourth level, it will not come entire its lifetime, it will not revolve there. It will eventually come to ground state after 10 power minus 8 seconds. While coming down to the first level, what will happen? It will emit some energy. E is equals to how much? H nu. Similarly, if the electron, there is one more electron which is revolving in third orbit, what will happen? Again, this electron will come and reach the ground state. Again, while coming down, what will happen? It will also emit some energy of radiation. E is equals to H mu. Similarly, there might be another electron which is revolving in second orbit. Again, while coming down, it will emit some energy to the, it will emit some energy while coming from higher energy orbit to lower energy orbit. So, based on this transition level, based on this transitional level of electron, we'll be getting different wavelengths. So, here what we'll be getting? We'll be getting one spectrum. Those spectrums are called as what? Spectral series in hydrogen atom. We are discussing regarding which atom? We are discussing regarding hydrogen atom. Now let us move on to our answer, how you are supposed to answer this question in the examination. Either you can consider these levels or you can draw the energy diagram. Drawing the energy diagram is very much easy. See here, I am drawing the energy diagram. You do the same thing. Let us consider different energy levels. Let us consider different energy levels. Here we are having different energy levels. As I am going up, the distance between two energy levels is decreasing. Carefully see this diagram. As I am going up, the distance between two energy levels is decreasing. As I am going up, the difference between two energy levels is decreasing. Let us assume these are the different energy levels. These are the different energy levels. The first level corresponds to what? N is equals to 1. Let me write down here. The first level corresponds to N is equals to 1. This level corresponds to N is equals to 2. This level corresponds to N is equals to 3. This level corresponds to N is equals to 4. This level corresponds to N is equals to 5. This level corresponds to N is equals to 6. This level corresponds to N is equals to 7. This level corresponds to N is equals to 8. Similarly, we'll be having some infinite levels, infinite energy level. And we know that the energy correspond to ground state will be how much? In ground state energy of hydrogen atom will be how much? It will be minus 13.6 electron volt. Here, what will be the energy here? Here the energy will be minus 13.6 electron volt. Now see here, what are the different types of spectral series we'll be getting in the hydrogen atom? This question you might have studied even in chemistry and even in your lower classes. When we know that wherever an electron jumps from higher energy orbit to lower energy first orbit, what will be happen? We'll be getting which type of series? We'll be getting Lyman series. Next we'll be getting Balmer series. Next we'll be getting Paston series. This question you might have already studied. So let us see here. First one, what are the different types of spectral series in hydrogen atom? So I can write. First one, Lyman series. First one, Lyman series. See here. When this, in which region does this series lie? It lies in UV region, ultraviolet region. It lies in which region? Ultraviolet region. First point. This is the first point you are supposed to write in Lyman series. Next point. Whenever an electron jumps from any of the higher energy orbit, any of the higher energy orbit to N is equals to 1, any of the higher energy orbit to N is equals to 1, then we will be getting what? We will be getting Lyman series. So let me draw this Lyman series here. An electron is jumping from any of the higher energy orbit to N is equals to which level? First level. Which type of series we will be getting? We will be getting Lyman series. So you are supposed to draw this diagram also. For drawing the diagram, you will be getting the marks. Don't leave the diagram. Marks are there for diagram also. So this is the energy level diagram for which series? Lyman series. So I will write here. This is which series? Lyman series. Lyman series. Now see here, let us write down the second point. Here, electron jumps from any of the higher level. I am writing initial levels of that as it can be 2, it can be 3 level, it can be 4 level, it can be 5 level, it can be infinite number of levels. But to which level it is jumping? To n is equals to 1, it is jumping. So I can write n final. N final is equals to what? 1. So what is our formula? Formula for wave number or wavelength is given as mu bar is equals to 1 by lambda is equals to mu bar is equals to 1 by lambda is equals to, we'll be getting actually r z square. But for which atom we are discussing? We are discussing for hydrogen atom. For hydrogen atom, what is the value of z? That for hydrogen atom, the value of z is 1. So this will become r of 1 by nf square minus 1 by ni square. 1 by nf square minus 1 by ni square. So what will be our formula? Our formula will become mu bar is equals to 1 by lambda is equals to r of what is the final level? Final level is 1 by 1 square minus 1 by ni square. Ni square. Now this initial level can be second level, this initial level can be third level, this initial level can be fourth level, or this initial level can be infinite level. So this is the things you are supposed to write in the answer. So how many types of spectral series we are having? We are having Lyman series, Balmer series, Bastian series, bracket series, and T-fund series. When we will be getting a Lyman series? In ultraviolet region, we will be getting a Lyman series. Whenever an electron jumps from any of the higher energy orbit to n is equals to 1, then which type of series will be getting? We'll be getting Lyman series. Similarly, what is the next series? You are supposed to write the same things in all the series. No need of by hearting all the answers. If you are remembering this one thing, you can write down the entire answer. What is the second series? The second series is Balmer series. Balmer series. And in which region does the Balmer series lies? It lies in visible region. Everyone knows that. It lies in which region? Visible region. So how do we get the Balmer series? We'll be getting the Balmer series whenever an electron jumps from any of the higher level to n is equals to 2. Any of the higher level to what? N is equals to 2. Which series will be getting? We'll be getting Balmer series. So something like this. Any of the higher level to n is equals to what? 2. What we'll be getting? We'll be getting Balmer series. As you are appearing for the examination, that's the reason I'm writing in the entire answer. Otherwise, I would have left this as a homework for you. This will become something like this. So which series we are getting here? We are getting this one as Balmer series. Balmer series. So similarly, what you are supposed to do? You are supposed to draw the we have done with Lyman series, Balmer series. You are supposed to draw the Bastian series, bracket series, and T-fund series. So see here, I am directly writing the answer here, but you are supposed to draw the diagrams. So here, what is the initial level? The initial levels can be Ni can be 3, 4, 5, 6, so on. And what will be NF? Final level will be how much? All the electrons are jumping from any of the higher energy orbit to which level they are jumping? N is equals to 2. So I can write final level is 2. So what will be our formula for Balmer series? It will become mu bar is equals to 1 by lambda is equals to R of 1 by NF. What is the value of NF here? 1 by 2 square minus 1 by Ni square. 1 by Ni square. I hope you are getting this. No, I am going to write the answer directly because next what you are supposed to do? You are supposed to draw the We are done with Lehman series. We are done with Balmer series. Next series will be what? Next series will be Paschen series. It will be somewhere here. Electron jumps from any of the higher energy orbit to n is equals to series 3. What here we'll be getting? We'll be getting a Paschen series. Paschen series. Lehman, Balmer, Paschen. Here n is equals to 4. We'll be getting bracket series. Bracket series. And for n is equals to 5, we'll be getting P fund series. P fund series. So here we'll be getting the transition line something like this. Any of the higher energy orbit to n is equals to 3. What will be getting? Paschen series will be getting. Any of the higher energy orbit to n is equals to 3. So these are the spectral lines, discrete spectral lines. See here. So this will be which series? This will be bracket series. This will be bracket series. And here we'll be having P fund series. Here we'll be having P fund series. So Lehman series lies in which region? Lehman series lies in UV region, ultraviolet region, UV region. And Balmer series lies in which region? Visible region. And Paschen series lies in which region? It lies in infrared region. Bracket series also lies in which region? Infrared region. And P fund series will also lie in which region? IR region. Now you are supposed to write the answer in the similar manner. Which series? What are the different types of spectral lines we are getting? We are getting Lyman series, Balmer series, Paschen series, bracket series, and P fund series. Whenever an electron jumps from any of the higher energy orbit to n is equals to 1, what we'll be getting? We'll be getting the Lyman series. Whenever an electron jumps from any of the higher orbit in higher energy orbit to n is equals to 2, which series we'll be getting? We'll be getting Balmer series. Balmer series lies in which region? Visible region. Whenever an electron jumps from any of the higher energy orbit to n is equals to 3, which series we'll be getting? We'll be getting Paschen series. Paschen series lies in which region? The spectral lines lies in which region? They lie in infrared region. Similarly, whenever an electron jumps from any of the higher energy orbit to n is equals to 4, we'll be getting bracket series. Whenever an electron jumps from any of the higher energy orbit to n is equals to 5, we'll be getting which type of series? P fund series. You are supposed to draw this diagram. After drawing this diagram, you are supposed to note down this thing. Write this Lehman series, Balmer series. You are supposed to write similarly for bracket series. You are supposed to write similarly for this series, Paschen series. Just change the number. In place of N1, NF, what you are writing in Lehman? 1 square. In Balmer, what you are writing? 2 square. In Paschen, what you will be writing? 3 square. In bracket, what will be writing? 4 square. In P fund, what will you be writing? You will be writing 5 square. I hope you understood this thing. So please do remember this answer. Very important answer for your annual examination. This question may be asked in your upcoming supplementary examination. I hope everyone understood this. Let us move on to the next question. We'll start a new chapter. We'll start a new chapter, that is ray optics. New chapter. Again, this chapter is also very much important for your supplementary examination or main annual examination. From this chapter, you will be getting around 6 marks, 1 SAQ and 1 VSAQ. Right now, we will be discussing SAQ. Once we are done with SAQs, we'll move on to VSAQ. So what is the new chapter that we are going to start today? That is ray optics. Ray optics. See here. I hope you might have already studied about ray optics in depth. We know that initially ray optics, we start with different types of mirrors. One will be plane mirror, then we'll be discussing regarding spherical mirrors. In spherical mirrors, we'll be again discussing regarding concave mirror and convex mirror. Then again, what we'll be discussing? We'll be discussing the laws of reflection. Then later on, we move on to the lenses. So right now, we are going to discuss one of the important concept for your annual examination. What is that? First concept that we are going to discuss in ray optic is Cartesian sign convention. Sign convention for spherical mirrors. For what? Which type of mirrors? Spherical mirrors. Spherical mirrors. Cartesian sign convention for spherical mirror. Cartesian sign convention for which type of mirror? Spherical mirror. Let us consider one spherical mirror here. I will try to draw a spherical mirror. Assume that this is our spherical mirror. Okay. Which type of mirror I am considering? I am considering a concave mirror. I am considering a concave mirror. What is this point called as? This point is called as pole. What is this point called as? This point is called as pole. And what is this axis? The name of this axis is what? Principal axis. So this is principal axis. The principal axis is passing through pole. Now see here. What are the Cartesian sign convention? This is very important for solving the numerical, even for determining different formulas or deriving different formulas. This Cartesian sign convention is required. Now everyone see here carefully. See here. Let us assume first point in Cartesian sign convention. First point. What is this? This point is called as pole. What is the first sign convention? All the distances should be measured. All the distances should be measured from pole. This is the first sign convention you should remember. We are having just 4 sign conventions. Just if you are able to remember, that's enough. What is the first thing? What is the first sign convention? All the distances should be measured from pole. See here, next sign convention. Assume that a light ray is coming in this direction. A light ray is coming in the forward direction. So see here, what is the second point? Distances measured in the direction of incident light should be taken as positive. Should be taken as positive. This is the second sign convention which you are supposed to remember. What is that? If the light ray is coming in this direction and it is going in this direction, we are measuring the distance in this direction. We should consider the distance measured to be positive or negative. We should consider the distance measured to be positive. So this distance is measured are what? Positive. Assume that light ray is coming in this direction and I am measuring the distance in this direction, in opposite direction. So what is the next point you can write? I can write that. What will be our third point? Distances measured in the direction opposite to the direction of incident light should be taken as negative. Should be taken as what? Taken as negative. So what are the things that we have discussed? We are left with only one single point. Always we should measure the distance from the pole. If we are measuring the distance along the direction of incident light, we should take this one as positive distance. If we are measuring the distance opposite to the direction of incident light, we should take the distance as negative distance. Third one, if we are measuring the distance above the principal axis, this is the principal axis. Now we are measuring the distance or height of an object above the principal axis. So what I should take? I should take the positive distance. This distance should be taken as what? It should be taken as positive. So what I can write? Fourth point, distances measured above the principal axis, otherwise you can write this like this also. The height measured above the principal axis should be taken as positive, and the height measured the height measured below the principal axis should be taken as negative. So you can write that like that also. Distances measured above the principal axis should be taken as positive, should be taken as positive. Instead of distance, I will write height. It will be better. Heights measured above the principal axis or should be taken as positive. And what is the next point you can tell? Heights measured below the principal axis. Last point, heights measured below the principal axis, below the principal axis should be taken as what? Taken as negative, should be taken as negative. So these are the 5 points you are supposed to remember in order to answer this question. What is that question? Cartesian, what are the Cartesian sign conventions for spherical mirror? So what are those sign conventions? What is the first convention? All the distances should be measured from the pole, and the distances measured along the axis of incident light should be taken as positive. The distances measured opposite to the direction of incident light should be taken as negative. And the height measured above the principal axis should be taken as positive. And the height measured below the principal axis should be taken as negative. I hope you understood this very basic question for your annual examination. This question you might have been studying from your 10th class itself. So let us move on to the next question. Let us go on to the next question. This is also a similar question which you have already studied in your lower classes. What is that question, sir? So the second question from ray optics that we are going to discuss is relation between focal length and radius of curvature See here. Relation between focal length and radius of curvature in case of spherical mirrors. So see here, just now we have discussed regarding concave mirror. What is concave mirror? Its shape will be something like this. This is called as concave mirror. This arrangement is called as what? This arrangement is called as concave mirror. Now see here. Let me draw this neatly. So let us consider this one to be a concave mirror. What is this? This is a concave mirror. This mirror is concave mirror. So what will be the center point of this mirror? This point is called as pole. What is this called as? This is called as what? This is called as pole. P-O-L-E. And the line which is passing through the pole is called as what? Principal axis. So this is the line which is passing through the pole, and this is called as what? This is called as principal axis. This is called as principal axis. Now see here. Let us consider a ray which is coming parallel to this principal axis. So this is a ray which is coming parallel to the principal axis. What will happen? What will happen after reflection? Here the reflection takes place. After reflection, what will happen? This light ray will pass through a point that is called as focus. After reflection, what will happen? This light ray will pass through a point. That point is called as focus. This point is called as what? Focus. So the distance between The distance between focus and pole is called as focal length. What it is called as? It is called as focal length. Now we are going to obtain the relation between this focus and radius of curvature, or focal length and radius of curvature. Now everyone see here carefully. We know that mirror is nothing but it is a part of one spherical mirror, spherical surface. It is a part of spherical surface. If it is a part of spherical surface, then it should have some center. Let us assume that here we are having center. This is center C. This is center C. Now carefully see here. Carefully see here. Mathematical part. You have already did this, but see here. Now from center C, what we are supposed to draw? We know that from center C, what we'll be considering? We'll be considering an imaginary line that is called as normal. An imaginary line that is called as what? Normal. If this angle is theta, what will be this angle? This angle will also be theta, because what is the loss of reflection? Angle of incidence should be equals to angle of reflection. If this angle is theta, then this angle will also become theta. Now carefully see here. If this angle is theta, then what will be this angle? This angle will also become theta. I hope you are getting this. A light ray is incident on a spherical mirror. After reflection, from which point it will pass? It will pass through a point of focus. Now here from center to that particular point of reflection, we'll be drawing an imaginary line. That line is called as what? Normal. We know that from loss of reflection, angle of incidence should be equals to angle of reflection. So this is angle of incidence theta. If this is angle of incidence theta, then angle of reflection should be theta. If this angle is theta, this should be theta. What is this entire angle? This entire angle will become 2 theta. So what will be this angle? This angle will become 2 theta. I hope you are getting this. So here this angle is theta, and what will be this angle? This angle will become 2 theta, because this entire angle is how much? 2 theta. This is something like this. Here, if this angle is 2 theta, then what will be this angle? This angle will also become 2 theta. Now see here carefully. Now what we are doing for mathematical calculation, we are drawing one perpendicular here. I am drawing one perpendicular here. Now let me write this as point A, this as point B, this as point P. And what is the distance between focus and pole? The distance between focus and pole is F. What is the distance between center of curvature and pole? This distance is called as radius of curvature. I hope you are getting this. I hope you are getting this. What is this? A parallel light, ray of light which is parallel to principal axis is incident on a spherical mirror. After incident, what is the phenomena taking place? Here the reflection phenomena is taking place. After reflection, the light is passing through where? It is passing through a point that is called as focus. And the distance between focus and pole is called as what? The distance between focus and pole is called as focal length. And the distance between pole and center of curvature is called as what? It is called as radius of curvature. Now let us start the mathematical part. Now everyone see here. See this. Everyone see here. From triangle ACP, I can write tan theta is equals to, what is the value of tan theta? Opposite by adjacent. What is the opposite side? It is AB divided by, what is the adjacent side? CP. CB. I hope you are getting this. If the angle is very small, here generally the angle will be small, because why we are considering the angle to be small? Because the rays which we will be considering are paraxial rays. I hope you might have studied about paraxial rays. So here, if the angle is very small, I can write tan theta as theta is equals to AB divided by CB. AB, opposite by adjacent, opposite by adjacent. I hope everyone know that. What is the trigonometric function? Tan theta is nothing but opposite by adjacent. What is the opposite side? AB is the opposite side. What is the adjacent side? CB is the adjacent side. So I can write tan theta is equals to AB by CB. If the angle is very small, I can write tan theta as theta. theta is equals to AB by CB. Now let us consider one more triangle there. Triangle AFB. Triangle what? AFB. So how much angle is here we are having? We are having angle 2 theta. So this can be written as tan 2 theta is equals to, what is that? Opposite by adjacent. What is opposite side? AB divided by what is adjacent side? FB. Now we know that if the angle is very small, if angle is very small, what I can write? I can write as tan 2 theta as 2 theta is equals to AB divided by FB. But what is the value of theta? What is the value of theta? What is the value of theta? The value of theta is AB by CB. Let us substitute here. 2 into AB divided by CB, that is equals to AB divided by FB. Now this AB and this AB get cancelled. So finally I can write, what I can write? 2 divided by CB is equals to 1 divided by FB. Now carefully see here. We are assuming that these 2 points, point B and point P, are very close to each other. The distance between them is very negligible. What we are assuming? We are assuming that the distance between B and P is very negligible, and we assume that this point B is at point P only. Then what this will become? See here, our final expression we are getting. What is our final expression? See here, everyone. 2 divided by CB. C point is here, B point is here. But what I said? B is on P itself. The distance between B and P is very negligible. So what is the distance from C to P? The distance from C to P is what? R. So this will become 2 divided by R is equals to 1 divided by, see here, FB. F is here, point B is here. What I am saying? The distance between B and P is very negligible. I can assume that the point B is at point P itself. So what is the distance between focus and pole? It is becoming F. It is F. So our final answer will be, the final relation for focal length and radius of curvature is given as R is equals to 2 into F. Radius of curvature, R is equals to 2 into F. So this is a very important question for your annual examination, supplementary examination as well. I hope you understood this topic. See here, let us see once again. Which type of mirror I have considered? I have considered a concave spherical mirror. I have considered a point at the center of the mirror. That point is called as pole. And the line which is passing through the pole is called as what? Which axis? Principal axis. Next, I have considered a ray which is coming parallel to the principal axis. After reflection, what is happening? It is traveling, passing through focus. And the distance between focus and pole is called as what? It is called as focal length. In the examination, you will be getting the question something like this. What is focal length? Obtain the relation between focal length and radius of curvature. So what you are supposed to define? You are supposed to define what is focal length. So what is the definition for focal length? Focal length is defined as the distance between focus and pole of that particular mirror is called as what? Focal length. Next, what we have did? We have considered an imaginary normal from center of curvature. If this angle of incidence is theta, then the angle of reflection will also be theta. From here, if this angle is theta, this angle will also become theta. What is this entire angle? This entire angle is 2 theta. So this angle will become also 2 theta. So how many triangles we are having? We are having 2 triangles. From the 2 triangles, what we are determining? We are determining tan theta. As the angle is very small, instead of writing trigonometric function, we are just writing what? Theta. The remaining thing is just mathematical, basic, simple mathematical calculation. I hope you understood this answer. Please note down these things. I hope you understood this answer. Let us move on to the next question. Next important question from this chapter. See here. Let us discuss the next important question from this chapter. That is critical angle and total internal reflection. Critical angle and total internal reflection. Total internal reflection. Let us discuss these two topics. Now see here. For these two phenomena to take place, one condition is required. What is that important condition required? That condition is the light must travel from denser medium to rarer medium. What is the condition required? In order to study about critical angle and total internal reflection, what is the condition required? The light must travel from denser medium to rarer medium. What is the first important condition? Here, important condition. Without this condition, this phenomena is not possible. What is that condition? The light must travel from denser medium to rarer medium. Denser medium to rarer medium. This is the first condition required. Without this condition, this phenomena can't be observed. What is the condition? Always the light must travel from denser medium to rarer medium. Now everyone carefully see here. By just understanding the diagram, you can write this answer. Now see here. Let me consider a surface which is separating two mediums. Assume this is a surface. This is one surface. Okay. Here we are having medium 1 of refractive index mu1. Here we are having medium 2 of refractive index 2. Here I am having one medium mu1 and here I am taking the medium as mu2. Assume that this is rarer medium. Which type of medium? I am writing this medium to be what? This is a rarer medium. Which type of medium? This is rarer medium. Rarer medium. And I am considering this medium to be denser medium. Denser medium. Now let us consider a source of light here. I am here having a source of light. This is our source of light. From this source of light, a light ray is going perpendicular to the surface. We know that whenever a light ray travels perpendicular to the surface, it will travel without any deviation. That is the reason a light ray originating from the source has traveled in the straight manner. Now carefully see here. What will happen? Let us see. Now see here. If you are able to understand the diagram, you can easily write the answer. See here. Assume that light ray is incidenting on the surface at one particular angle. The light ray is incidenting on this particular surface at one particular angle. I am calling that as angle of incidence. This is angle of incidence. Now see here, light ray is going from denser to rarer medium or rarer to denser medium. The light ray is going from denser medium to rarer medium. Whether it will move away from the normal or towards the normal, whenever a light ray goes from denser medium to rarer medium, it will move away from the normal. Whenever a light ray comes from rarer medium to denser medium, it will move towards the normal. So here, the light is going from denser medium to rarer medium. So definitely what will happen? It will move away from the normal. So this angle is called as angle of refraction. This angle is called as angle of refraction. See here, I am considering one more ray with a little bit increase in angle of incidence. What I did, I have increased the angle of incidence. Again, I am drawing a normal. Again, the light ray is going from where to where? Again, the light ray is going from denser medium to rarer medium. Assume this is the next angle of incidence. What will happen? Whether the light ray will move towards the normal or away from the normal. Again, the light ray will move away from the normal. Assume that it is moving somewhere here. Something like this. This is called as angle of refraction. Now, what I did, I have further increased the angle of incidence. I have further increased the angle of incidence. Now, I am further increasing the angle of incidence. Now, let us see what will happen. This is our imaginary line, which is called as normal. Now, this is our angle of incidence. Here I am writing, this is our angle of incidence. Now, what will happen? Let us see. the refracted ray makes 90 degree with the normal. The refracted ray makes how many degrees? 90 degree with the normal in which medium? In rarer medium. This condition, this angle of incidence is called as critical angle. Everyone see here. This angle of incidence is called as critical angle. I am representing that critical angle with theta c. What does theta c represent? Theta c represents critical angle. So at one particular angle of incidence, what is happening? The refracted ray is making an angle of 90 degree with what? Normal. In which region? In rarer medium. This region, this angle is called as what? Critical angle. Let us understand what will happen if I further increase the angle of incidence. Let us see what will happen if I further increase the angle of incidence. I have increased the angle of incidence further. I have increased the angle of incidence further. Let us see what will happen. Again, what I am supposed to draw? I am supposed to draw a normal here. So this is angle of incidence. This is angle of incidence greater than which angle? Greater than critical angle. Now what will happen? Instead of the ray going in rarer medium, it will again turn back in which medium? In the same denser medium. See here what has happened? As the ray is going from denser to rarer medium, it is moving away from the normal. It is moving away from the normal. Finally, what is happening? It is making an angle of 90 degree with respect to normal in which medium? Rarer medium. That angle of incidence is called as which angle? That angle of incidence is called as critical angle. If I further increase the angle of incidence, if the angle of incidence is greater than critical angle, what will happen? The ray will be reflected in the same medium. The ray will be reflected in the same medium. This phenomena is called as total internal reflection. This phenomena is called as what? Total internal reflection. I hope you understood this diagram. If you are able to understand this diagram, you can easily write down the answer. What I did, I have considered two different medium. One is called as rarer medium, other one is called as denser medium. Whenever a light ray, what is the condition for critical angle and total internal reflection? The light must go from which medium to which medium? Denser medium to rarer medium. So whenever a light ray is going from denser medium to rarer medium, what will happen? The refracted ray will move away from the normal. As I go on increasing the angle of incidence, the refracted ray angle will also increase. At one particular angle of incidence, what will happen? The refracted ray will make an angle of 90 degree with respect to normal in which medium? Rarer medium. Then that angle of incidence is called as which angle? That angle of incidence is called as critical angle. If I further increase the angle of incidence, if the angle of incidence is greater than critical angle, the ray will be reflected in the same medium. Then that phenomena is called as what? It is called as total internal reflection. Let us assume here the refractive index of the medium is 1. Mu1 is equals to 1. Here the refractive index of medium mu2 is mu. Mu2 is mu. First of all, I'll be writing the definition for this. Then I'll be writing one equation. Carefully see here. What is the first thing we are going to discuss is critical angle. At a particular otherwise I will start from this here. When the light ray must travel from denser to medium. Okay. At a particular angle of incidence in which medium? In denser medium. In denser medium, the refracted ray makes how much angle? Refracted ray makes 90 degree with the normal, 90 degree with the normal. In which medium? In rarer medium. In rarer medium. Full stop. This angle of incidence, this angle of incidence is called as what? Is called as critical angle. Critical angle. I hope you understood this definition and the meaning of critical angle. What is the first important condition? The light ray must travel from which medium to which medium? Denser medium to rarer medium. At one particular angle of incidence, what is happening? The refracted ray makes an angle of 90 degree with respect to normal in which medium? Rarer medium. Let us determine the value of this critical angle theta c. Now we know that we are aware of the Snell's law. What is that Snell's law? Mu2 divided by mu1 is equals to sine I divided by sine R. Mu2 divided by mu1 is equals to sine I divided by sine R. See here. Here, let me take this one as. Here I am having refractive index. Mu2 is equals to 1. Here I am taking refractive index. Mu1 is equals to mu. See here, what will happen here? Mu2, what is the value of mu2? The value of mu2 is 1. And what is the value of mu1? The value of mu1 is mu. That is equals to sine. What is the angle of incidence? Here I am taking the angle of incidence as theta c. And what is the angle of refraction? Refracted ray makes how many degrees? 90 degrees. So this will become what? Sine 90 degrees. So what is the value of sine 90 degrees? The value of sine 90 degrees 1. So from here I can write sine theta c is equals to 1 by mu, or you can also write theta c is equals to sine inverse 1 divided by mu. You are supposed to write down this formula. First of all, what you are supposed to do? You are supposed to write down this definition without doing all these things, but you are supposed to write down this formula. You will be getting the marks, 2 marks for writing this definition. Okay. What is the definition for critical angle? This definition you are supposed to write, and don't forget to write this condition. This condition is very important. If you don't write this condition, you will lose the mark. The light should go from which medium to which medium? The light should go from denser medium to rarer medium. I hope you understood this critical angle. Let us move on to the next thing, that is total internal reflection. What will be the definition for total internal reflection? If the angle of incidence is greater than critical angle. What is the second one? Total internal reflection. If the angle of incidence in denser medium is greater than critical angle, the light gets reflected in the same medium. The light gets reflected in the same medium. Full stop. This phenomena is known as total internal reflection. This phenomena is known as what? Total internal reflection. So let us end today's class here itself. So what are the things that we have discussed in today's class? We have started with the last concept of atom, and we have discussed regarding different types of spectral series in hydrogen atom. What are the different types of spectral series in hydrogen atom? Lyman series, Balmer series, Paschen series, Brackett series, and Punt series. Lyman series lies in which region? Ultraviolet region. Balmer series lies in which region? Visible region. Remaining all the series lies in which region? They all lie in infrared region. Next, we have started a new chapter that is called as ray optics. In ray optics, first of all, we have discussed regarding the Cartesian sign convention. Then we have moved on to the next important question, that was the relation between focal length and radius of curvature. Later on, we have discussed regarding what is that? This is the last thing, critical angle and total internal reflection. So we'll be discussing the remaining questions tomorrow. I hope you understood this class. We'll meet tomorrow. Thank you.